All right, so section 9.6 is going to be over alternating series. And you'll know if you have an alternating series because they will all contain the term, right, of -1 raised to some stuff, okay? So it could be just n, it could be n plus 1, right? It could be any kind of expression. But what this does is it alternates the terms between positive and negative. So we've actually seen a couple of alternating series already. We looked at like geometric series that can alternate because the value r can be positive or negative. You even had one on your quiz. So, but if you don't have an alternating series that looks like a geometric or some other known series we know how to deal with, there's actually a test we can apply to figure out if that thing converges. So there's a couple different ways that we can express -1. There's more than the two I'm about to show you, but the ones I'm going to show you are the most common. So if n equals 1 and the alternating term in your series is -1 to the n, then what that means is all the odd ordered terms in your series will be negative. And all the even ordered terms in your series will be positive. But if we have -1 to the n plus 1, right, what that does is it shifts the negative sign over one place. So if you've got this situation, now the odd terms will become positive and the even terms will become negative. So remember, when I'm saying odd and even, I mean the even ordered terms. So like A3, A4. Guys, you gotta be off your phones. Seriously, no phones. So odd terms, even terms, right? And we mean the ordered terms. So let's look at a quick example of something we've looked at before. So even though this is a geometric series and we can deal with it directly, right, we can rewrite this to make it look like the form of an alternating series. So I'm allowed to say, well, that's just -1 to the n over 2 to the n. So if I rewrite this series, I can pull the -1 to the n out front, and now it has the form of a traditional alternating series. So for this series, if you were looking at it, right, and we started with the form on the right, most likely we would turn it into the guy on the left because a geometric series is really easy to integrate. But if we look at the first couple of terms, we can see it matches the pattern that I gave you above. So the even terms are positive, the odd numbered terms are negative. So the rule of exponents that you want to make sure you remember is if you have stuff being multiplied together and it's being raised to the n, we're allowed to write it as x to the n, y to the n. And conversely, if we start with x to the n, y to the n, we can group them together. We can do the same thing when we divide. So x to the n over y to the n is the same thing as x over y to the n. So that's true for any exponent or expression that we give. So let's go over what the alternating series test does. So the alternating series test is actually not that hard of a test to perform. You just have to make sure that the series meets the 3 conditions that are required. So for an alternating series, so I'm going to abbreviate this, right, as AST. So that way whenever we just jot down AST, we know what we're meaning, so we don't have to keep writing that out every time. All right, so for the alternating series test, we need a sub n to be greater than 0. right, so we need a sub n to be 0, but remember when we're talking about the alternating series, a sub n is not the whole entire expression, okay? An alternating series by default has that -1 to the stuff out front. So remember we said we give you the two most common types, but I can tweak these exponents and they're still alternating series as long as they're -1 to some stuff. So what we're calling a sub n now is just everything that's not the alternating part. So it's the rest of the expression. So if you have rewritten it and factored the -1 out front and everything else is positive, then you can proceed and try to meet the other two conditions. If everything else is not positive, then you need to double check and see if you can take the thing that's making it negative and work it into that -1 term. So if we remove the -1 and we look at everything else and it's positive, the series will converge if the limit of that stuff goes to 0, just like with all series, right? But more importantly, the terms are decreasing for all n, okay? Now, for all n, right, it's great if it's true for every value n, but remember, this is an infinite series, so we're only looking at things going out to infinity. So if the terms are a little wonky on the front end, maybe they trade back and forth, like who's bigger and who's smaller, but just like we saw earlier when we compared 1 over n to 1 over 2 to the n, we saw that once you hit the fourth term, 1 over n, or 2 to the n, or sorry, my bad. We compared 1 over 2 to the n to 1 over n factorial, right? And we saw that once we hit that fourth term, n factorial took off and overtook 2 to the n. So when we say for all n, if there is a finite number n, like 4, 5, where we know after that moment this inequality is true, then that still holds. We can still use it because we only care about things going off to infinity. So let's look at an example and see how to apply this test. So this is the alternating harmonic series. So we know that the harmonic series 1 over n diverges. We've looked at that a couple of times. So the alternating harmonic series, we can perform the test. So the first thing you want to do is identify what a sub n is. So a sub n, is all the stuff that's not the -1. So clearly these guys are going to be positive for all n because we're only plugging in positive values of n. So it meets the first condition. The limit as n goes to infinity of 1 over n is 0. So it meets the other condition. Then we have to see, well, does the limit, or are the terms reducing over time? So if we write the nth plus 1 term, we get 1 over n plus 1, and then the nth term is just 1 over n. So clearly, right, if the denominator of a fraction gets bigger, the whole fraction gets smaller. So we can actually tell right away that this is true for all n. So since all three conditions were met, this series converges. So one of the things you have to make sure when you're applying these tests that we're doing going forward, you have to demonstrate that you know the three conditions and that you're showing me these conditions. All right? So let's look at another one. So we just looked at this series above. Right? We said this is the alternating geometric series. So we know this converges because it's a geometric series, but we could also apply the alternating series test. So here, your a sub n term is just 1 over 2 to the n. That's going to be positive. The limit as n goes to infinity of 1 over 2 to the n is in fact 0. But are the n plus 1 terms getting smaller? Right? So if I want to compare a sub n plus 1 to the a sub n, right, I'm allowed to split this apart, and I'm allowed to say, well, this is 1/2 to the n, times 1/2, and I want to compare that to 1/2 to the n. So the 1/2s to the n cancel on both sides. So what I get is 1/2 compared to 1. Well, 1/2 is clearly less than or equal to 1. And since none of the math I did required multiplying or dividing by a negative number, that means the sign of the inequality never flipped, and you can backfill it all the way to the beginning, and this condition was met, so the series converges. So what tends to intimidate people about the alternating series test is you got to remember 3 things, but they're really easy things, like once you kind of get the hang of it. All right, let's look at an example of a series that doesn't have the natural form of an alternating series, but we can tell it's alternating, and I'll show you how you rewrite it to put it in that form. All right, everybody good here? Okay. All right, so let's look at this. All right, so this is -2 raised to the n minus 1. So what I'm allowed to do here is that -2 is the same thing as saying -1 times 2, okay? So just like we said, if you have x times y raised to something, I can say x to that thing, y to that thing. So if I factor out the -1 in the denominator, well, since it's -1, 1 and -1, it doesn't really matter if they're in the numerator and denominator. You can move them back and forth because they don't affect the value of the equation. So I can actually pull a -1 to the n minus 1 out front, and then I'm just left with 2 to the n minus 1. All right, does everybody see I'm allowed to do that? Because -1 can be written as either 1 over -1, or we could write it as -1 over 1. So you can move 1s and -1s in and out, back and forth in the denominator without changing the value, okay? So now that we have it in the form that's alternating, right, our a sub n term is just n over 2n minus 1, and that will all clearly be positive. So this is why this first condition is like this. When you have to rearrange it, you want to make sure you did it properly. So as long as this stuff is all positive, you know you got rid of all the negative stuff in the right way. All right? Then we want to take the limit as n goes to infinity of n over 2 to the n minus 1. So this is definitely a L'Hopital situation, right? You have infinity over infinity, but the derivative of the numerator is just going to be 1. But we know the exponential will keep coming back when we take the derivative of it. So we can kind of just say it's 0. Right? I'm kind of okay with that. Like, that's a pretty basic one. Right? So that condition's met. So now what we need to see, well, how does the nth plus 1 term compare to the nth term? So in the numerator, we're plugging in plus 1. But look what happens if I plug an n plus 1 into this exponent. I'm going to get n plus 1 minus 1, so the 1's cancel, so I just end up with 2 to the n in the denominator. Then we're going to compare that, right? So I just use a little box because I'm not sure what the inequality is, and I'm just going to fill them back in when we're done. All right, so what I want to do here is I want to group the exponentials together and then group the things that aren't exponential together. So I'm allowed to cross multiply. So what I'm really going to do is I'm going to multiply both sides by this, which will put it in the numerator, and then I'm going to divide both sides by n plus 1, which will bring this over to the denominator. So now I can say 2 to the n minus 1 over 2 to the n over, right, we're going to compare that to n over n plus 1. Then, right, I can split up this numerator, and I can say, well, that's just 2 to the n times 2 to the negative 1 over 2 to the n. And my 2 to the n's are going to cancel. Furthermore, 2 to the minus 1 is just 1/2. So really, I need to do this. So you only have to carry this math out until you get to a line where the inequality is clear. The minute you can clearly put the sign in, you're done. So you don't have to keep going all the way down until you get a constant. So since we're starting at values of 1 and I have a constant on one side, let's just throw a couple values into the right-hand side and make sure this works. So when n is 1, I get 1/2 on the right. That's equal. That's allowed, right? If I plug in 2, I get 2/3. 2/3 is bigger than a half, right? And then I'm going to get 3/4, right? 4/5. So we can say right here, this is less than or equal to. So now I can backfill, right, my inequality. The condition is met. So this series converges by the alternating series test. Does anyone not see the inequality? Because these can be tricky. Everybody understand what I did? And we know because we started at 1, 2, 3, it was true for all n. So it worked out fine. All right, so let's look at one that doesn't work out quite so nicely. Okay, let's see what happens when the test fails. Because we have 3 conditions, there's 3 different things that could go wrong for us, right? And you have to know by what's going wrong, that will tell you whether it diverges or whether the test is just inconclusive and we have to try something else. Right, so let's look at n from 1 to infinity of -1 to the n plus 1 times n plus 1 over n. So the a sub n term is just this. So that is positive, so that condition is okay. Well, what are we going to get when we take the limit of that term? One. That's not 0, so we have a problem, right? Furthermore, we need to go ahead and test the third condition. Let's see if that passes or fails, because this will give me a clue on whether I'm diverging or whether the test is just inconclusive. So if I look at the n plus 1 term, when you plug n plus 1 into the numerator, you really just get n plus 2. And when I plug n plus 1 in the denominator, I just get n plus 1. And I want to compare that to n plus 1 over n. So then I'm allowed to cross multiply like I did before. So n times n plus 2 is n squared plus 2n. When I multiply n plus 1 by n plus 1, I get n squared plus 2n plus 1. Well, I'm allowed to subtract n squared from both sides, so those go away. I'm allowed to subtract 2n from both sides, and those go away. So I end up with 0 and 1. So even though this is in fact decreasing for all n, right, it failed the limit part of the conclusion. So what do we know about every series in order to converge? The limit's got to go to 0. So on this series, because it failed the limit test, we know it's going to diverge to infinity. Not only is it going to diverge to infinity, it's going to alternate the series. The list of terms are going to turn into 1, -1, 1, -1, 1, -1. And we already talked about the series of -1 to the n, where it's just bouncing back and forth, diverges because the limit doesn't even exist for that, right? So you don't want to forget that it's actually alternating. So this series, right, fails the first condition, passes the second condition, but we can conclude that it diverged. So when you're taking the limit of the nth term, whatever value comes out of the limit, that's what all the terms as you approach infinity become. right? So if this were just the series n plus 1 over n, we would have taken the limit, gotten 1, and said diverges, because you're just summing 1, 1, 1, 1, 1, 1, 1. But you got to remember, because it's alternating, it's going to go 1, negative 1, 1, negative 1. If it had summed to 2, if the limit had been 2, it would have been 2, negative 2, 2, negative 2, okay? And so if you look at the partial sums, depending on how many terms you're counting, they'll either sum to 0, they'll sum to 1, or they'll sum to negative 1, depending on where you started counting from. So the 1 and the negative 1 will wipe each other out, and then you'll have an extra 1, right? Or the negative 1 and the 1 will wipe each other out, and the next term was a negative 1. So the partial sums are never settling on a single value, so this thing has to diverge. So can we find the sum of an alternating series, right? We can sum up geometric series and get the actual number. We saw we can sum up telescoping series and get the actual number, because we're just left with the first term and the last term. We just have to add those together. But what about an alternating series? So the short answer is not exactly. I mean, there's some advanced methods we might be able to do to get close to the number, but we can actually come up with a really close estimate of what the sum approximately is. So what we do, right, recall, right, that S sub n is simply the sum of the first n terms. So the remainder of the series, if you only sum up n of them, then everything you didn't sum up, right, that's still going to infinity, that's just what's left over, and that's what the remainder is, right? So the remainder at that value n is simply the total sum of the whole series minus the partial sum that you came up with. So there's a theorem, and what we're going to do is we're going to write the theorem down, because the words are a little confusing, and then I'll explain what all that craziness means, all right? So by calculating the remainder that's left over, we can actually come up with a really good range of values to see what the sum is. So the first thing is you have to know the series converges, otherwise the sum doesn't exist at all. Right? This is for alternating series. This is a whole lot of words to explain a very simple equation. If you can't stay off your phones, you're going to have to leave. I'm not kidding. It's very rude. So, does everybody understand that the remainder is just the sum minus the first n partial sums? Is that clear with everybody, right? You just take the total sum, subtract off the first n terms, and the remainder is just everything left over going on to infinity. So, if you take the absolute value of both sides of that equation, you end up with this stuff right here, right? And the reason we're using the absolute value is because this series is alternating back and forth between positive and negative terms. So I just want to know, what is the magnitude of the stuff on the left, and does it equal the magnitude of the stuff on the right, right? And what we're saying is, if the terms are reducing, then this remainder will be less than or equal to the next term where you cut off n. So if we sum the first 5 terms, then the remainder for the rest of the series at n equals 5 is less than or equal to a6. Okay? So let's look at how we can actually use this. So I'm not going to ask you on the exam to calculate remainders for me, okay? But you really need to have this in your notes because it's a very important idea. So if you're going into like anything applied, like engineering, computer science, anything that involves programming, right? What we're doing, if you have an infinite series of numbers, you can think of the error as, the remainder as sort of like the appropriate area. Like I can't get to the exact sum, but it's okay if I'm off by like 1% or 3%. So by calculating the remainder and then figuring out what that value n is that gets you that remainder, well, we know how to work with finite things, and that's easy to program. You can just say, well, sum this from 1 to 6, right? Or from 1 to 3. And we can actually program that in quite easily. So let's look at a series and see if we can approximate the sum. So let's look at 1 over n factorial. So we're going to let n be 6, all right? So that means I need to list out the first 6 terms. So we know this series converges because it's going to pass the alternating series test, right? Our a sub n is 1 over n factorial. Those are all positive. The limit of 1 over n factorial goes to 0. And we can see that the terms are reducing, right, as they keep going. So we know this guy converges. So that means let's calculate the partial sum of the first 6 values. So that's 1 minus a half plus a third, oops, sorry, not a third, a sixth. 3 factorial is 6. All right, minus 1 over 24 plus 1 over 120 minus 1 over 720. All right, so I've done this math for you so we don't have to waste time. And this sums to 91 over 44. 91 over 144. And if we approximate that using decimals, we get 0.63194. So the theorem, right, says, well, if I take the sum, subtract S6 from it, that equals the remainder at 6. And so R6 means that would be the sum of 7 through infinity, right? And this should be less than or equal to A7. So the remainder, right, A7 is 1 over 7 factorial, which is 5,040. So that works out to be 0.0002. So the remainder is no more than that number, but it could be a little bit less than that number. So if we go back to this original equation, I can rearrange it and say, well, remember, this is the absolute value. So I don't know if it's a positive or a negative value because it depends on how we indexed the series. So the sum of the series should be no more than the first 6 terms plus that remainder, but no less than the first 6 terms minus that remainder. So we've taken care of the positive and the negative case. So when we plug in our values, we get 0.63174 and 0.63214. So now I have a range that's pretty small that says the sum is somewhere between these two values. And so this is, like I said, not a small thing, and it's one of the areas where you would apply this concept in an applied math class. And you would actually want to calculate these remainders. And we might use it, like I said, for error. We might use it for probability. I mean, there's a lot of different ways we can construct a series to do this, right? So if you're in statistics, you can create a series that's calculating probability for you. So this is just not, like I said, it's a very important idea. Any questions? All right, so I'm not going to ask you to calculate this for me, but like I said, I want it in your notes. It's a very important proof. All right, so the other thing that happens in this series that we can test for, that'll make testing alternating series really easily, is the idea of absolute versus conditional convergence. So remember, for absolute convergence, right, the name is in the title. It means you're probably going to take the absolute value of something, right? And if the absolute value converges, then the series will converge absolutely, right? Let's use the word in the proof. So it's really important in here that you're not just focusing on the computation, because if you really spend a little time learning the concept, you can save yourself a lot of work. Because if you conceptually understand these ideas, you can test for some of these things right up front, and if it converges, you're done, right? If it diverges, you can shut the problem down quickly. So this theorem, right, says the definition of absolute convergence says if the series, right, of the absolute value of A sub n converges, then the original series must converge as well. So what we mean by this, it doesn't make any sense to take the absolute value if the original series was all positive to begin with, right? Because the absolute value of a positive number just returns itself. So clearly you want to apply this when things are alternating. But the A sub n here in this theorem means the whole expression. But if you take the absolute value of -1, you get 1. If you take the absolute value of 1, you're going to get 1. So if you only look at the positive section of the series, right, and you add up all of those terms and keep them positive, that is the maximum possible sum you could ever achieve because everything's positive, right? If we alternate the terms, right, the sum should be less than or equal to that, because think about 1 over n, right? You put in 1 and then you remove a half. Then you put in a third and then you remove 1/4, right? But if you add 1 plus 1/2 plus 1/3 plus 1/4 and you keep them all positive, you're going to get a larger number, okay? So what we're saying here is let's test the worst case scenario, right, where everything's positive and the pile is as high as it's ever going to get. If that stuff converges, then clearly the alternating stuff will converge because it will be less than. So this is sort of, in a way, another version of the direct comparison, right? If you can find something bigger that converges, right, than you'll get squashed, right, and you'll converge too. And so that's what we're doing here. Let's take the biggest possible thing that converges. Now, what's really important the converse is not true. And the most basic example to prove this to you is the alternating harmonic series. So If an alternating series converges, you cannot assume the positive version of it will converge too, right? So the example is, right, this guy converges, we just saw it. Oops. But this guy diverges, right? And we prove this by using the integral test. So if I take the absolute value of this alternating series, that becomes positive 1, and I end up here. So that's what I'm saying. You can't assume if the alternating series converges that that converges. But if all the positive terms converge, the alternating series will definitely converge because its sum will be less. Okay? Any questions on that? No? You guys are being really quiet today. Okay. So what we're going to do starting, what's today, Wednesday? Okay, so Friday's lecture will pick up right after this, and this should say conditional convergence. Friday's lecture will pick up and we'll define what conditional convergence is, and then we'll do a bunch of examples where we kind of see how do you say something converges absolutely versus conditional. And if we finish that section, we might dip into the ratio test, and then on Monday's lecture we'll definitely finish the ratio test. But I have a handout that I want to give you on Monday, so I brought that, so I'm going to give that to you, and then I'll post it on ELC as well for the online students. But what this handout is it summarizes on the front page. Let me get it out. I'll show you guys on the thing. So this is going to be your new best friend when you're doing series. So a lot of times, how do you put all this stuff together and keep track of it? Because it's a big old mess. I couldn't do it either. So one of the things, like I remember when I first started like working in Milledge Hall, they had this weird flow chart. I mean, it was just like, it was right, but it was just, it made you want to just scream. All right, so I worked really hard on organizing this, so the students that have been using it seem to like it. So here's what's on the front page. So it's the guidelines for calculating if a series converges or diverges. And I've given you a list of 4 questions, and you want to treat this list like a checklist. You want to go through it 1 through 4, and what it does is it's designed to take you through the path of least resistance. Test for the obvious stuff up front, and then we work our way down to the harder tests, because there's no reason in doing the complicated stuff if we can eliminate the easy stuff first. So the first thing that it always asks you to verify is, does the original limit go to 0? If it doesn't, shut the whole thing down, you're done, okay? If it does go to 0, well then you still have to test for convergence. You have to keep going, right? So then it says, well, is the series one of the special types? So can we, and remember, you might have to rearrange it to get it into this form, right? So if you recognize the geometric, that's the condition on convergence. If it's a p-series, right, these are the conditions on convergence and divergence. And if it's telescoping, this is how we test, right? If those don't work, can we use one of the following tests? So the integral test, you look, can the series be written as a function of x? That's continuous, right? If it's an alternating series, it should have this in there, right? We haven't learned the ratio test yet, but the ratio test, you look for factorials. A factorial is always going to mean ratio test, okay? We haven't talked about the root test yet, but if the series is a whole bunch of stuff raised to the n, then we're going to apply the nth root test, right? And then at the very bottom here, if none of those things apply, well, can we compare it favorably to one of the special types? So remember, direct comparison requires the inequality, and you have to make sure you set the inequality up the right way. And the limit comparison is where we stack them and do the limits. And remember, it's a little more robust, so we can flip the limits right or left. So just remember, one or more tests may apply. It doesn't matter if you pick a test different from what I picked. As long as it's appropriate, you can do it. So there is more than one way to get here. So now, the front page are the 4 questions. The back page is this nice handy little chart that has all the tests listed out, what the form of the series is, the conditions for the convergence, conditions for divergence, and then a couple little comments if we need. But notice here I labeled number 1, number 2, number 3, number 4. If the answer to any of the first 4 questions are yes, these are the rows on the table that you want to go through to verify that you're meeting the right conditions. So this is made so you can just kind of flip it back and forth. So This thing will be really great when you're just looking at a bunch of random series, and it's just a good way to organize your thoughts, your process, and make sure you're being really logical and rational when we're approaching this. All right, so I'm going to hand these out once we start the quiz because I want to get the quiz problems down. And so we're going to do the second part of quiz 11. Oops. Oh, it won't let me scroll. So this will be quiz 11, part 2. And remember, any valid method that I've showed you is appropriate. Like anything we've learned, because these quizzes kind of become cumulative in a way. Like, you know, there may be more than one way to do some of these, unless I tell you you have to do a specific thing. So this is quiz 11, part 2. This one I want back on Wednesday because I will be here. We've been here for this. We're here today. But the 2 we're going to have for Friday and Monday, you can turn in next Friday. All right, so this one is, this is question 3 because we're continuing on from the last quiz. All right, we want to determine if this converges or diverges. So remember, you could maybe use the integral test. You could maybe do a limit comparison or a direct comparison. Anything we've done up through now would work, except for today's stuff. So the first one. And part of the trick on a lot of these is you may have to rewrite some of them to get them in a way that looks more familiar.